leading to tetrahedron complex and dsp2 hybridization wherever it is possible, leads to the square planar geometry. So these are the concepts that you are already aware of. Now, the valence bond theory had certain shortcomings, failures. It could not satisfactorily, address the issue of the electronic spectra of the coordination compounds, or in simple terms, I should say the color of the coordination compounds was not explained by the valence bond theory, and also the magnetic properties could not be satisfactorily explained by the valence bond theory. And for to explain these things and other issues, the crystal field theory was developed. It was developed by two gentlemen separately in 1929 and 1933, and the premise of the theory is that there is a Coulombic interaction between the center metal ion and the ligands, as in primarily as the electrostatic interaction. And we'll come to the detail. Let's go to the presentation. I hope my screen is shared now, Hannah.
Yes, sir. Yes, sir.
कंप्यूटर में प्रॉब्लम है कुछ. स्लाइड डिस्प्ले हो गई?
यस सर.
एक मिनट, कोई बच्चा एडमिट ज्वाइन कर रहा है, जस्ट मिनट. आयशा मलिक. ठीक है, मेरी स्लाइड्स विजिबल है?
Yes, sir.
Yes, sir.
So the crystal field theory was developed by the Hams back in 1920, and Van Vleck had done a lot of work in the magnetic chemistry. You will read about Van Vleck equation, etc., in your next semester when you discuss the magnetic properties of coordination compounds. He had done a lot of work on the to explain the magnetic properties of the compounds and develop equations which could satisfactorily correlate the experimentally observed values and the theoretical predictions about the magnetic moment observed in the coordination complexes. So he also contributed to the development of this theory. So it is originally developed for studying the optical properties of crystalline solids. That's why the name goes crystal field theory. They gave this name because as I said, valence bond theory could not satisfactorily explain the color of the coordination compounds, particularly in the solid state, and therefore this theory was named as crystal field theory because it was developed for studying the optical properties, color properties of the crystalline solids. So what is the high point of the valence bond theory was it could rationalize geometry and magnetic properties to some extent, but the serious shortcomings of the valence bond theory was that it could not explain the electronic spectra of the complexes, why there are compounds are colored, and how many bands would be observed in the electronic spectrum of the coordination compounds, number of bands, position of bands, intensity of bands. These are three parameters in the the electronic spectra of the coordination compounds. You will read about these things in the next semester, that there are three features of the electronic spectra of the coordination compounds. Number one is what is the position of bands, what is the lambda max. Number two is how many bands are observed. It's not only the one band, some compounds show 2, 3, 4 bands. and how many bands, what is the position of bands, then nature of the bands, or bands sharp or broad, and third is what is the intensity of the bands. These issues were not explained by the by एक second, somebody is nobody is there. So these issues could not be, explained by the valence bond theory, and why some ligands lead to high spin and some ligands lead to low spin complex, or what the term that was used in the valence bond theory was inner orbital and outer orbital complexes. So it could not explain why some ligands, form, sort of inner orbital complexes, and which would be also called low spin complexes, and why certain ligands form high spin complexes or outer orbital complexes. And third thing which it could not, valence bond theory could not explain, that low spin D6 complexes are octahedron complexes particularly, are exceptionally kinetically inert. What we mean by exceptionally kinetically inert means that these complexes do not undergo substitution reaction, and if at all they undergo substitution reaction, they undergo, the rate of the reaction is very slow, deadly slow, and right, not so slow. Other complexes undergo reaction in seconds, nanoseconds, microseconds. These compounds could react in seconds. So slow reaction occurs, but it occurs slowly. So that means that there is some kinetic hindrance or energy barrier which prevents these D6 complexes. It was a blessing in disguise at that moment that D6 complexes, cobalt 3 complexes, or iron 2 complexes in the low spin configuration, rhodium 3 complexes, or ruthenium 2 plus complexes. They were used to study the mechanism of the substitution reactions of the coordination complexes. ऐसा क्यों है कि उनको, क्योंकि उस टाइम टेक्निक्स, फास्ट रिएक्शंस को स्टडी करने के लिए आपको बहुत फास्ट टेक्निक्स चाहिए, बहुत फास्ट इक्विपमेंट्स चाहिए जो नैनो सेकंड्स में कंसंट्रेशन का वेरिएशन को मॉनिटर कर पाए। तो क्योंकि शुरू में इतनी टेक्निक्स डेवलप नहीं थी, आप सिंपल टेक्निक्स यूज कर रहे थे कि कंसंट्रेशन, काइनेटिक्स में क्या करते हैं कि टाइम के साथ कंसंट्रेशन किस तरह चेंज हो रही है उसको मॉनिटर करा जाता है। ऑब्वियसली अगर कंसंट्रेशन बहुत फास्ट चेंज हो जाए टाइम के साथ तो आप उसको फॉलो नहीं कर पाएंगे नॉर्मल टेक्निक से, तो फिर कंप्यूटराइज कोई एडवांस टेक्निक को, स्पेशल टेक्निक को जो सेकंड्स में ही रिएक्शन को फॉलो, मतलब कंसंट्रेशन चेंज हो सेकंड्स में उसको फॉलो कर पाए। नॉर्मल टेक्निक्स यूज करके हम ये चीज मॉनिटर नहीं कर सकते। और ये कॉम्प्लेक्सेस क्योंकि बहुत स्लोली रिएक्ट करते थे, इसलिए इनकी कंसंट्रेशन वेरिएशन टाइम के साथ स्लोली चेंज होती थी, और इनको हम मॉनिटर कर सकते थे, और इन्हीं को स्टडी करके मैकेनिज्म्स डेवलप कराए गए। कोऑर्डिनेशन कंपाउंड्स किस मैकेनिज्म से रिएक्ट करते हैं, SN1 है या SN2 है, एलिमिनेशन हो रही है कैसे हो रही है, कंसर्टेड मैकेनिज्म है या पहले लिगेंड चला जाता है फिर इनकमिंग ग्रुप आता है। ये सारी बातें जो है तभी मुमकिन है, आप पता कर सकते हैं जब आप रिएक्शन को फॉलो कर पाए। आप ये क्या नाम है, कोई आपने आइसोटोपिक सब्स्टिट्यूशन की, फिर उस स्टेप को फॉलो कर पाए कि वो स्टेप के स्लो है या फास्ट है बाकी स्टेप्स के मुकाबले में। तो मैकेनिज्म को डेसिफर करना, वो काइनेटिक्स इसमें बहुत इंपॉर्टेंट पार्ट प्ले करता है। स्टीरियोकेमिस्ट्री दूसरा चीज है, काइनेटिक्स एक इंपॉर्टेंट सेंट्रल रोल है काइनेटिक्स का। तो इसलिए ये जो D6 कॉम्प्लेक्सेस थे ये बहुत स्लोली रिएक्ट करते थे, वो एक ब्लेसिंग इन डिस्गाइज थी कि उनको स्टडी करके हमने सारे मैकेनिज्म्स डेवलप करे। लेकिन this could not be explained why certain complexes with certain electronic configuration like T2G6EG0, that is the low spin configuration of the octahedron complexes, why these complexes were slow in reaction. They do not undergo substitution reaction as fast as other configurations go, and this is related to what we mean by what we will later on discovered as crystal field stabilization energy, that these complexes have extra stability by virtue of a special configuration of non-bonding electrons. Remember, these d electrons are not involved in the bonding, they are non-bonding, and they are not responsible for the thermodynamic stability of the complex. They are giving special stability, special kinetic stability to the complex by virtue of the energy which we call crystal field stabilization energy. So valence bond theory obviously could not explain this kinetic inertness of the cobalt 3 complexes. Cobalt 3 complexes in cobalt 3 can form high spin as well as low spin complexes. लेकिन उसके नीचे जो दूसरा मेटल है वो है रोहोडियम. Rhodium invariably forms low spin complexes always with all kinds of ligands, right? और उसके नीचे है iridium. Iridium also never forms high spin complexes. It always forms low spin complexes. Similarly, जो दूसरा ग्रुप है आयरन वाला ग्रुप, उसमें +2 ऑक्सीडेशन स्टेट आयरन 2+ जो है वो D6 है, राइट? तो अगर लिगेंड स्ट्रॉन्ग फील्ड और कुछ लिगेंड के साथ वो हाई स्पिन कॉम्प्लेक्स बनाता है, कुछ के साथ लो स्पिन भी बनाता है. लेकिन आयरन के नीचे रुथेनियम है और रुथेनियम के नीचे ओस्मियम है. रुथेनियम एंड ओस्मियम ऑलवेज फॉर्म लो स्पिन कॉम्प्लेक्सेस, दे नेवर फॉर्म हाई स्पिन कॉम्प्लेक्सेस. So this is true for 4d and 5d elements. As the d orbital size of the d orbital becomes 4d and 5d orbitals are large in size, they have larger space extension in the space, so they feel larger repulsion. So even weak field ligands create lot of repulsion, and they generate low spin complexes. They never form 4d and 5d transition elements, never form high spin complexes. So this possibility of high spin and low spin is only possible in the 3d series. So let's come to the crystal field theory. Overall, the energy of this is the basic principle, basic fundamental cornerstone of the theory, that overall energy of a complex, coordination complex, is governed by Hamiltonian. Hamiltonian is an energy operator. You must have read in this semester itself the quantum mechanics, the importance of Hamiltonian, that when it is multiplied with any wave function, it generates energy values. So coordination compounds Hamiltonian is contributed by three things. Number one Hamiltonian is ligand field term. It is the energy term generated by interaction of the metal ion and the ligands. And number two is interelectronic repulsion within the metal ion, which is inherent in any multi-electron atom. The electrons mutually repel each other, and there is the contribution from the exchange energy. And third is spin orbit coupling. When you have multiple electrons, each electron has its own spin angular momentum, and each electron also, if it is occupying a d orbital or p orbital, it has orbital angular momentum, and the two angular momenta then couple, and we have another interaction that's known as spin orbit coupling. So these three Hamiltonians overall generate the energy of an coordination compound. Crystal field theory postulates that the most appropriate value of H1, the first one, the ligand field term, the ligand field, you can calculate the Hamiltonian H1 by assuming that metal ion and the surrounding ligands are point charges, and so that H1 is purely of the Coulombic nature. It's an electrostatic interaction between the point charges. If you assume that the ligands are point charges, if it's a negatively charged ligand, if it is a neutral ligand, then it's the negative dipole of the molecule which is orienting towards the metal ion, and therefore you can assume that it's a point charge, it's a negatively charged unit, and metal is a positively charged center. And so there is an electrostatic interaction between them. The ligands approach metal because metal is positively charged and ligand is negatively charged. So they are interacting in a simple Coulombic fashion, electrostatic interaction, positive negative interaction. So ligands come closer and closer to the metal, and in the process the d orbitals feel that repulsion, because d orbitals hold negatively charged electrons and ligands have negative charge. So there is negative repulsion between d orbitals and the d orbital electrons and the ligand electrons. Right. So that H1 is primarily constituted of a Coulombic interaction. So electric field gradient developed by ligand. Yes. So, so what happens that when a group of ligands approach central metal ion, they generate an electric field surrounding the metal ion. If the symmetry of this electric field is spherical and symmetrical, then all d orbitals which hold electrons will feel repulsion and will interact with those ligand charges and will be raised in energy by same amount. However, if the electric field generated by the ligands is not symmetrical, is asymmetrical, and there is more electric field in certain directions and there is less electric field in certain directions. If that is the situation, we call it electric field gradient. Gradient means when there is not uniform charge distribution around the metal ion. Suppose ligands approach the metal ion in a spherical situation, spherical environment, then each orbital will feel same repulsion. The electric field will be uniform in all the directions. But this never happens. That the directions in which the ligands approach metal ion does not have spherical symmetry. It has either octahedron symmetry or tetrahedron symmetry or the square planar symmetry. So which is less than the spherical symmetry. So because of this asymmetric distribution of the ligand charges around the metal ion, the electric field that is generated by the ligand point charges is not uniform, is not symmetric, it is asymmetric, and we call it in one term an electric field gradient is developed by the ligands, right? So electric field gradient developed by the ligands, it should be ligands, interacts with the metal ion and H1 takes care of this interaction. And Hamiltonian is taking care of this interaction between the electric field gradient of the ligand and the d orbitals. So H2 governs the Coulombic repulsion again between electrons and their exchange energy. H3 accounts for the coupling of the spin and orbital angular momenta of the d and f electrons, right? So in an isolated gaseous atom, the d orbitals are degenerate. This is what we know, that when you have an free atom, particularly in the gaseous state, we say that the d orbitals, all 5d orbitals, have same energy. So when the same metal ion is engaged in the complex formation, ligands approach towards the metal ion, they perturb this electric field around the metal ion due to the electron cloud on the ligand, generating repulsive force between ligand electrons and the metal d electrons. So what is the consequence? Consequence is that d orbitals feel asymmetric electric field, or we call it electric field gradient, and degeneracy of the orbital is consequently lifted. Some d orbitals feel more repulsion and some d orbitals feel less repulsion. Those who feel more repulsion are raised in energy, and those who feel less repulsion are comparatively, lowered in energy. If all the ligands approach metal ion in a symmetrical or spherical fashion, no electric field gradient will be there, and spherical or symmetrical electric field will not split the d orbitals. It simply raises the energy of all the d orbitals to some extent, but degeneracy is maintained because of the repulsion between the ligand electrons and the d electrons. The d orbitals will be raised in energy, but then all d orbitals will be raised to the same extent, and the degeneracy will be maintained. However, if the symmetry of the ligand charges is not spherical or is not symmetrical, because the d orbitals inherently are of two kinds: those which are aligned in between axes, this is dxz, this is dxy in between axes, this is dz square along the x axis, along the z axis, and in xy axis, this is dxz again in between the axis, and this is x square minus y square along the axis. So there are two orbitals which are aligned along the axis and three orbitals which are aligned in between the axes. So however, if the ligands approach in a symmetric fashion, electric field gradient is generated, and consequently the degeneracy is lifted. So different orientation of the d orbitals is responsible for this sensing of the asymmetric field, because some d orbitals are oriented along axis, some are oriented in between axes. So there is different perception of the different d orbitals, different orientation of the d orbitals. D orbitals interact with the electric field gradient. EFG means electric field gradient differently. Why? Because there are two sorts of d orbitals. D orbitals along the axis, they are dz square and dx square minus y square, and d orbitals in between axes, dxz, dyz, and dxy. So d orbitals having lobes in the direction of the ligands are repelled to a greater extent than those not in the direction of the ligands. So result is that d orbitals will split, and splitting into two states is called crystal field splitting. This process of splitting is called crystal field splitting. Right? Now let's go to the octahedral crystal field. You have 6 ligands approaching ligand in a non-spherical, environments, non-spherical, symmetry, which is of course highly symmetrical geometry, but not as symmetrical as the sphere. So 6 ligands approach along the 6 directions which are along the axis. 2 ligands approach along x-axis, plus x-axis and minus x-axis, 2 along y-axis, plus y and minus y, and 2 along z-axis. So there are 6 ligands, all of them lying along the coordinate axis, Cartesian coordinate axis, x, y, and z. 2 of them lying on the x-axis, 2 of them lying on y-axis, and 2 on z-axis. Dz square minus y square and dz square orbitals, which are aligned along the axis, obviously will feel more repulsion. They are directed along these axes and feel more repulsion, and their energy will be raised, whereas the dxy, dxz, and dyz orbitals, which lie in between the axes, they are comparatively they feel less repulsion, and therefore they will be lower in energy. So thus d orbitals split into T2G and EG. T2G set is called the lower energy set is called T2G. T2G is an symmetry symbol that we will study in the next semester. T stands for, right now, T stands for triplet. So there are 3 orbitals, triply degenerate, and E stands for doublet, doubly degenerate. dxz, dx square minus y square, and dz square are doubly degenerate. So this is known as orbital degeneracy. So splitting of the orbitals occurs in such a way that overall energy of the system remains constant. Since the total increase in energy of the EG orbitals and total decrease in energy of the T2G orbitals from the center, from the barycenter, is same. So crystal field energy is represented by delta 0 or 10 decros. Right? So this is degenerate 3D atomic orbitals. So this is when the ligands are far away, they are approaching, and the metal ion is not sensing this asymmetric field. They are raised in energy. This is known as barycenter. And when the 3D orbitals are split, this is the situation. If the electrostatic field created by the point charges of the ligand is spherical, this is the situation. The electric field is spherical. The orbitals will be raised in energy, but they will not undergo splitting. The energies of the orbitals in 3D orbitals are raised uniformly. If the electric field gradient generated by the point charges of the ligands is octahedron, the energy of the electrons in the 3 orbitals that point directly at the ligands is raised with respect to that in the spherical field, while the energy of the electrons in the orbitals that point in between ligands will be decreased or lowered with respect to sphere. So the magnitude of energy that is raised from the barycenter is same as magnitude of depression in the energy, so that overall there is no change in energy. So change in energy of the electrons occupying d orbitals of metal ion when the later is in the octahedral field, the energy changes. So crystal field energy is represented by delta 0 or 10 decals. It defines the crystal field strength of the ligand. If the ligand, if the splitting is large, then this delta 0 will have the large value, or 10 decal will be the large value. Higher the strength of the ligand, greater will be the value of delta 0 at 10 degree. In the case of octahedron complexes, T2G orbitals go down by minus 0.4 delta 0, and EG orbitals are raised by plus 0.6 delta 0. So because there are two orbitals in the EG, so and three orbitals in the T2G. So T2G are lowered by zero point 0.4 decals. So zero point 0.4 delta 0 into 3 is equal to 1 point minus 1.2 delta 0. Zero point 0.6 into 2 is again plus 1.20. So overall, zero energy. There is no change in energy because the T2G set is lowered by same amount, EG set is raised by same. That's what we mean by overall there's no energy change. So this is upper EG set, and this is T2G. This is 0.0 plus 0.6. Every electron that goes here will raise the energy of the system by 0.06 delta 0. And every electron that goes here will lower the energy of the system by minus 0.4. Okay, delta O0, delta O. Suppose there are two electrons only in the complex, and both of them will go obviously to the T2G. So the energy of the system will be minus 8.4 and 0.4, 2.4 minus 0.8 delta 0. This is also equal to, in terms of the decal, it is 6 decal and minus 4 decal, and that is equal to 10 decals or delta 0. These are the orbitals which are directly confronting the ligands and therefore raised in energy, dx square minus y square and dz square. And these are the orbitals which are not pointing directly in this direction of the ligands, and therefore they are not raised in energy. So let's look at the electrons in the orbitals. So for octahedron complexes, electrons are filled from lower energy orbitals. That's the normal sequence of the orbitals. That lower orbital energy, lower orbital has to be occupied first. When it gets filled, then you have to go to the higher orbital, and you follow the Ahwaz principle, Pauli's principle, and Hund's rule. These are three rules that you have to follow when you put electrons in these orbitals. So maximum spin multiplicity, that's the Hund's rule, that you have a degenerate set of orbitals and you have to place electrons in them, place maximum electrons with parallel spin. So that is the maximum spin multiplicity should be adopted. So up to D3 there is no problem, because the first electron will go to the T2G, the second will also go to the T2G. First one will go here, second one will go here, third one will go here. The fourth one has a choice. It can go either here or it can come and join this. So if it joins this orbital, there will be two electrons in this orbital, and that is repulsion between the two electrons within the same orbital is measured by a parameter known as pairing energy. So there is, on one hand, there is pairing energy, repulsion between the electron in the same orbital, and on the other hand, there is delta 0, the crystal field splitting. So it depends upon which factor is dominating. If pairing energy has larger magnitude than the crystal field splitting, then electrons will not like to pair up. It will go to the higher orbital here. However, if the delta 0 is larger than the pairing energy, then electron will certainly go here. So there is a competition between these two things. So for D3, up to D3, there is no problem. You have T2G1, EG0. For D1 configuration, you have a complex which has D2 configuration, T2G2, EG0, and then D3 has T2G3, EG0. At D4, there are two choices. Number one is that electron goes, fourth one also goes into T2G. That is when delta zero has larger value than the pairing. Pairing does not generate as much disturbance as putting electron into EG. And if it is reverse thing, is delta zero is less than pairing energy, then electrons avoid pairing. Electron will go to the higher energy orbital, EG orbital. So this spin pairing energy versus delta zero. So this is, if the pairing energy is, less, delta zero is more than pairing energy, you generate low spin complex. This configuration will have only 2 electrons, unpaired electrons. This will have 4 unpaired electrons, and this is known as high spin complex. These type of complexes are generated by strong field ligands, which have large crystal field splitting energy, and these sort of complexes are generated by weak field ligands, which have less crystal field splitting energy. So this is for D4. If the delta zero is large, then the pairing energy, then electrons will get paired up here. The EG orbital will remain empty. The reverse thing, when delta zero is less than pairing energy, electron will go here. Similarly, for D5, you can have all electrons in the lower orbital if the delta zero is larger than pairing energy. If reverse is true, that pairing energy is large, then each orbital will have 1 electron, 3 here and 2 here. Similarly, we have D6. This is low spin complex of the D6, where crystal field splitting energy is large than the pairing energy. So all electrons get paired up into the T2G set. And reverse thing is happening in the high spin complex. The ligand field is weak, so electrons avoid pairing. So you give 2 electrons here. The last one, the sixth one, will have to get paired here. So there are 4 unpaired electrons in the high spin situation. There is no unpaired electron in the low spin configuration. So this is diamagnetic, this is paramagnetic. And then you have D7. D7 again, you have 6 electron here and 1 here. This is when pairing energy has smaller value than the crystal field splitting. If the reverse is true, that pairing energy is more, then you have 5 electrons in the lower orbital and 2 electrons in the higher orbital. So for D8, D9, and D10, there is only one option. That is for D8, it is T2G6, EG2. For D9, it is T2G6, EG3, and D10, it is T2G6, EG4. So we conclude that D1, D2, and D3, D8, D9, and D10, there is no choice of high spin and low spin. There is only one configuration. Whereas the choice of high spin and low spin occurs only for D4, D5, D6, and D7. These are the 4 configurations where you have both high spin as well as low spin complexes. Now, the spectrochemical series, it was found that there are certain ligands which, given a choice, a series of complexes were studied in which the metal ions were kept same, oxidation state was same, and coordination geometry was same. Only the nature of the ligand was changed from one ligand L1 to L2, and then the magnetic properties, etc., were followed, and it was found that some ligands generate lot of crystal field splitting and some generate less crystal field splitting under same conditions. So the crystal field theory primarily based on the arrangement of the ligands around the central metal ion and effect of the ligand field generated by the ligands. The electrons in the ligand generate an electric field gradient which leads to splitting of the d orbitals. So ligands are classified as strong or weak based on their position in the spectrochemical series, and this is the series that was expected on the basis of crystal field theory, that iodide should generate a weak field as compared to bromide, bromide weaker than the sulfide, thiocyanate nitrogen negative, somewhat stronger than sulfide, then chloride, then nitrate, then fluoride, much stronger ligand, and then OH negative, and then oxalate, and then water, stronger than OH negative, then thiocyanate S, then methyl cyanide, then ammonia, then ethylene diamine, bipyridine, phenantholine, nitrite, triphenyl phosphine, cyanide, and carbonate. So example is that you have cobalt hexamine complex 3 plus, octahedron cobalt same metal ion oxidation state +3. Here also cobalt octahedron complex same oxidation state but ligand different, This is high spin paramagnetic and this is low spin and diamagnetic. So these are the ligand field splitting parameters. So look at the D3, chromium, which does not have high spin, low spin situation. If you have chloride, these are the values 13.7 into 10 raised power 3 centimeter inverse. So chloride has lesser crystal field splitting than water. Water, although neutral, generates in crystal field splitting, which is larger than the chloride. And ammonia, much more stronger than water. And ethylene diamine, little bit, stronger than the ammonia because of the chelation effect. And then cyanide, larger than the ethylene diamine. Look at D5, where you have high spin and low spin combinations possible. Manganese plus and iron 3 plus, both are D5. This is 7.5, and for iron it is 11.0 because the charge is different here now. It's not only the ligand is same, metals are different, right? And their oxidation states are different. So therefore difference. So if you nullify the effect of metal, you go from this to this, 7.5 to 8.5. Here the metal is same, coordination number is same, oxidation state is same, but the nature of the ligand is same. It's chloride 7.5, water 8.5, and ethylene diamine 10.1, and cyanide 10.30. Similarly, iron, you can see for cobalt, low spin, water, low spin, then ammonia, low spin, then ethylene diamine, and then cyanide, all low spin complexes and increasing. Rhodium 3, which is below the cobalt 3, you can see larger crystal field splitting. For water, it is 20.7. For cobalt, rhodium, it is 27. For ammonia, it is 22.9. It is 34 for rhodium. So say different metal ions in the same group, having same oxidation state, same geometry, but then ligand is from the metal is from the 4D series. Similarly, ethylene diamine cobalt complex is 23, and for rhodium it is 34. So cyanide is 45. So look at the nickel; it has also changing values. So that is all about the crystal field theory for the octahedron complexes. We will talk about its consequences tomorrow. What are the information that could be rationalized?